In 6.3, we're going to continue to work on solving linear systems, and now we're going to use a new technique, and this text is calling it adding or subtracting. In the previous text, they called it by using combination. I think combination is a more explicit description of this, because what we're going to do is we're going to combine the two equations in our linear system into one single equation. But we are going to do it by adding or subtracting, so both are quite accurate, but you might hear me say combination as we talk in class. That's just a habit of mine. So again, we're going to solve systems of linear equations. Our vocabulary is the same, systems of linear equations. And when we talk about how you go about this, we want to add or subtract the equations to eliminate one variable. And this is the important part, to eliminate one variable. That's what we did when we did substitution. If you remember, we start with a linear system in two variables, and by solving for one variable and then substituting into the other equation, we eliminate that variable, right? So the goal is always to go from having two variables to having one so that we can find the value of that variable. So then we solve the resulting equation for the other variable, and then we substitute back into the original equation, just like we did when we were doing substitution. So when you take a look at this set of equations, you can see that if I add the two equations together, negative 5y and positive 5y, these are going to, they're opposites, so these are going to eliminate the variable y when I add them together. So this is perfect, it's all set up for me. I'm just going to go ahead and proceed and add them together. So I have negative 3x plus negative 4x is negative 7x. Negative 5 plus 5, that's 0. And negative 7 plus 14 is 7. And then when I divide either side by negative 7, x will be equal to negative 1. Okay, so I know that x is equal to negative 1. And now when I plug back into one of the original equations, I can do either one. I'm going to do the second one. Negative 4 times negative 1 plus 5y is equal to 14. So this becomes 4 plus 5y is equal to 14. If I subtract 4, 5y is equal to 10, so y is equal to 2. And there's my solution. Okay, let's take a look at another example. All right, so now in this particular problem, I've got 4x and 4x, and I have negative 9y and 3y. So what I'm going to do now is I'm going to subtract. Okay, so 4x minus 4x is 0, right? Negative 9 minus 3 is negative 12y. And negative 21 minus negative 9 is negative 12. When I divide either side by negative 12, I'll get y is equal to 1. That's great. Okay, so we're going to go back and we're going to plug 1 in place of y. So I'll have 4x plus 3 times 1 is 3 is equal to negative 9. So 4x will be equal to negative 12. So x will be equal to negative 3. Negative 3. Okay, and that's my solution. Now, sometimes they don't give you the equation so nicely put together, right? Remember, when we were working on this, I have my x's in a column, my y's in a column, and my constants in a column, and this is the easiest way to work. Here, they've got things all kind of jumbled up and out of order. So the first thing I'm going to do here is I'm going to add 2x to either side of the second equation. Okay, and now you can see that I could do either subtraction or addition, right? If I subtract, the x's will drop out. If I add, the y's will drop out. I'm going to add and get rid of the y's, so I'll get 4x here. The y's drop out, and I'll have negative 11 plus negative 13 is negative 24. When we divide by 4, x will be equal to negative 6. If I take that negative 6 and plug it back up into one of these other equations, I'm going to plug it into the second one. Y is equal to negative 2 times negative 6 minus 13. Well, negative 2 times negative 6 is 12 minus 13. So y is equal to negative 1. So my solution here is negative 6, negative 1. Right? When we take a look at this one, everything is all ordered up just fine. I could subtract if I wanted, but I'm actually going to do something that is really more related to the next section we're going to be working on. And what I'm going to do instead is I'm going to get rid of all of the fractions as well, just because I know a lot of you don't like working with fractions, and there are ways to get rid of the fractions. Okay, so I could definitely subtract right now. Well, actually, let's go ahead and do it that way. I'll show you in the next section how to get rid of the fractions. But if I multiplied every term in this equation by 4, I get x minus 2y equals negative 28. And if I multiplied every term in this equation by 4, I'll get 32x minus 2y equals, let's see, 120 plus 32 would be 152, negative 152. And you might prefer to work with these equations instead. So sometimes if you're looking at a problem that's got a bunch of fractions and you want to get rid of them, you can by multiplying both sides of the equation by the least common denominator. Now you notice I could have multiplied the top equation by 2, but I multiplied it by 4 so that I did the same thing to the 1/2 y in both equations and they stayed the same. Okay, but let's just go ahead and let's go ahead and work with this as fractions, because that's a good habit too. So this is 8 is 32 fourths. 32 fourths minus 1/4 is 31 fourths x. Negative 1/2 minus negative 1/2 is going to be 0. And negative 38 minus negative 7 is going to be negative 31. Now I'm going to multiply both sides of the equation by the inverse of this fraction. And the 4 cancels with the 4, and the 31 cancels with the 31, and I just get x. And the 31 cancels with the 31, not with the negative, and I just am left with negative 4. So x is equal to negative 4. I know that in my solution, x is negative 4. Now I can plug that into either of these equations. I'm going to plug it into the second one, because I can see that negative 4 is going to eliminate that 1/4. And all the other numbers will be smaller than if I worked in the top equation. So I've plugged it in. And 1/4 times negative 4 is negative 1. And when I add 1 to either side, I'll get negative 1/2 y is equal to negative 6. And then I'm going to multiply both sides of the equation by the inverse of this. The inverse of 1/2 is 2, and it needs to be negative. So I'm multiplying both sides of the equation by negative 2. So y will be equal to positive 12. 12. Okay, so you've noticed also that I'm allowed to multiply both sides of the equation always by the same number, right? We have to make sure we arrange things in columns to make things work out a little better. And then let's take a look at what this is like applied to a real world kind of concept. So now we've got a rowing crew. So this is a 4-person crew team here in our little picture. And they race a rowing shell in a river. So they go upstream, which is against the current, and downstream, which is with the current. So here the current will slow me down, and here it will speed me up. The shell moves upstream at a speed of 4.3 meters per second and downstream at 4.9, which makes sense. The speed of the current remains constant. Okay. Use the models below to write and solve a system of equations to find the average speed of the shell in still water and the speed of the current. Okay, so I know that let's say that the current is C, and let's say that the speed of the crew is S. So I know that S plus C, right, that's when I'm going downstream, is equal to 4.9 meters per second. And I know that my speed minus the current, that's when I'm going upstream, is 4.3. You can see that if I add these equations together, the C, the speed of the current, will drop out, and I'll get 2S is equal to, let's see, this would be 8 and then 9.2. So when I divide by 2, S is equal to 4.6. So that's my speed of the crew. If I plug back in, I can find the current. So if I have the speed, I'm sorry, my mistake, I should have plugged that in. I'm going to use the first equation. So the speed, which is 4.6, plus the current is equal to 4.9. So the current is equal to 0.3. Right? And that's how I work the whole thing out. That's it for 6.3.